Welcome to G Fun Facts Online. For centuries, our understanding of magnetism has been elegantly simple, neatly filed into two primary categories. First, you have ferromagnets. These are the friendly magnets on your refrigerator. All their internal magnetic moments, or spins, point in the same direction, creating a strong external magnetic field. Then you have their counterparts, antiferromagnets. In these materials, the spins alternate, pointing in opposite directions, perfectly balancing each other out. The result is no net external magnetic field. Ferromagnetism and antiferromagnetism. For decades, this was the complete picture. But what if I told you that in the quantum world of crystals, a third magnetic state was quietly waiting to be discovered? A state that combines the best of both worlds and shatters our fundamental understanding of magnetism. This isn't science fiction. This is the dawn of altermagnetism. Altermagnetism is a brand new class of magnet that intriguingly combines the key features of its famous cousins. It has the zero net magnetization of an antiferromagnet, meaning it doesn't stick to your fridge. But it also has the spin-polarized currents of a ferromagnet, a property that is the bedrock of modern data storage and a field called spintronics. This combination was once thought to be fundamentally impossible. Its discovery isn't just a new footnote in a physics textbook. It's a key that unlocks a new era of technological possibilities, promising to reshape everything from computers to medical devices. So how did we miss this for so long, and how was it finally found? The story starts not with an experiment, but with pure theory. A team of visionary theorists, including Libor Smejkal, Jairo Sinova, and Tomas Jungwirth, began to question if the traditional magnetic binary was truly complete. Between 2019 and 2021, they dove deep into the complex symmetries that govern how electrons behave inside crystals. They had a key insight. In a standard antiferromagnet, the oppositely pointing spins are typically related by simple symmetry operations, like shifting them in space or inverting them. But the theorists wondered, what if in some crystals, the antiparallel spins were connected by a rotation? What if you had to physically rotate the crystal lattice in your mind to get from a spin pointing up to a spin pointing down? This seemingly subtle difference in symmetry turns out to have profound consequences. Their calculations predicted that this unique rotational symmetry would create a very peculiar electronic structure. While the material as a whole would have no external magnetic field, the energy bands of the electrons inside would be spin-split. This is a hallmark feature of ferromagnets, and it means that an electron's energy and momentum depend on its spin. But in an altermagnet, this only happens for electrons moving in specific directions. In other directions, the spin splitting vanishes, and the material behaves like a normal antiferromagnet. This alternating, direction-dependent spin behavior is what gives the phenomenon its name, altermagnetism. This theory, laid out in a series of groundbreaking papers, essentially drew a treasure map for experimental physicists. It said that altermagnets could exist, and they would have incredible properties like carrying spin-polarized currents, all while remaining magnetically silent on the outside. The race was on to find one. The theoretical predictions ignited a flurry of activity, and the breakthrough came in early 2024. Multiple teams reported compelling evidence, and one of the star materials was manganese telluride, or manganese 2 telluride. Traditionally, manganese 2 telluride was considered a classic, even boring, antiferromagnet. But its specific crystal structure made it a prime suspect for altermagnetism. To prove it, researchers used a sophisticated technique called angle-resolved photoemission spectroscopy, or ARPES. Think of ARPES as a superpowered camera for electrons. It works by shining high-energy light onto the material, which knocks electrons out. By measuring the precise energy and angle of these ejected electrons, scientists can create a direct map of their behavior inside the crystal. The results were stunning. The ARPES scans of manganese telluride revealed a distinct spin splitting in the electronic bands, a clear, undeniable signature of altermagnetism that matched the theoretical predictions perfectly. But that wasn't the only proof. Another material, ruthenium dioxide, or RuO, also stepped into the spotlight. Experiments on this material demonstrated another key altermagnetic feature, the anomalous Hall effect. The normal Hall effect is simple. If you run a current through a conductor and apply a magnetic field, a voltage appears on the sides. But in ferromagnets, this effect can happen even without an external magnetic field, thanks to their own internal magnetization. This is the anomalous Hall effect. Finding a significant anomalous Hall effect in ruthenium dioxide, a material with zero net magnetization, was another smoking gun. It was a property that should NT be there, unless, of course, it was an altermagnet. These experimental confirmations transformed altermagnetism from a theoretical curiosity into a tangible reality. So we've established altermagnets are real, but what makes them so special? It comes down to a unique, best of both worlds combination of properties. First, as we've said, they have zero net magnetization. This lack of a stray magnetic field is a massive advantage. In high-density data storage, like hard drives or MRAM, the magnetic fields from neighboring bits in a ferromagnetic material can interfere with each other. This limits how closely you can pack them. With altermagnets, that problem disappears. You can design devices that are far more dense and also much less vulnerable to interference from external magnetic fields, making them more robust. Second, and this is the revolutionary part, altermagnets can generate and conduct spin-polarized currents, just like a ferromagnet. A spin-polarized current is a flow of electrons, where most of the spins are pointing in the same direction. This is the fundamental principle behind spintronics, a field that uses the electron's spin, not just its charge, to store and process information. The ability to do this without the messy stray fields of a ferromagnet is a game-changer for spintronics. Third, there's speed. Altermagnets are predicted to have much faster magnetic dynamics than ferromagnets. The speed at which you can flip a magnetic state is crucial for memory and logic devices. In ferromagnets, this speed is limited to the gigahertz range. Altermagnets, however, are expected to operate at terahertz frequencies. That's potentially 1,000 times faster. This isn't just an incremental improvement. It's a leap into a new performance category. So what does this all mean for technology? The promise of altermagnetism is vast. The most immediate impact will likely be in spintronics and data storage. Current magnetic memory, or MRAM, is great because it remembers data even when the power is off. But it faces challenges with density and energy use because of those stray ferromagnetic fields. Altermagnets offer a solution. MRAM built with altermagnets could be denser, faster, and far more energy efficient. The terahertz operating speeds could lead to a new generation of high-performance computers that are orders of magnitude faster than anything we have today. The potential also extends beyond conventional computing. The fast, efficient switching of altermagnets could be perfect for neuromorphic computing, which aims to build chips that function like the human brain. Their stable magnetic states could even provide a new platform for qubits, the building blocks of quantum computers. And this isn't a niche phenomenon. While ferromagnetism is relatively rare, found in only a few elements, theory predicts that altermagnetism could exist in over 200 candidate materials, including insulators, semiconductors, metals, and even superconductors. This gives scientists a huge, diverse playground to find and engineer materials for specific applications. Now, while the future is incredibly bright, there are challenges. One of the biggest hurdles is simply making the materials. Many of the predicted altermagnetic effects are subtle and can be hidden by tiny defects or impurities. Scientists need to perfect methods for growing large, high-quality, single-crystal altermagnetic materials. Another challenge is control. For a device to work, you need to be able to switch the magnetic state easily and efficiently, using something like an electric field or a laser pulse. Researchers are actively exploring how to do this. The discovery of altermagnetism marks a true paradigm shift in our understanding of one of nature's most fundamental forces. It shatters the old binary and reveals a richer, more complex magnetic world than we ever imagined. With its unique combination of stability, spin control, and incredible speed, altermagnetism offers a tantalizing glimpse into a future of technology that is faster, smaller, and more powerful than ever before. The journey has just begun, and the coming years are sure to be filled with exciting discoveries as we continue to unravel the mysteries of this new and extraordinary magnetic state. Thanks for listening to G Fun Facts Online.